Hello class, and welcome to lecture number 5, Measurement Design, for our Quantitative Research Methods class. Today we're going to do some review of our measurement design, and then you'll have a few in-class activities to complete to take care of your participation points for this week. So the first thing we'll do is review simple linear regression and correlation from last week. Remember, null hypothesis testing is one paradigm that we use in research, and it can be the way in which one person might frame a research project. So remember, the purpose of null hypothesis testing is to reject the null in order to support the alternative hypothesis. So the alternative hypothesis might be that there were more shark attacks this year than last year, and our null hypothesis would be that there was not more shark attacks this year than last year. Type 1 error would be to reject the null when the null is true in the population. This is a false positive, so it would conclude that there were more shark attacks this year when in fact there were not. Type 2 error is when we fail to reject the null when the null is false in the population. So this is a false negative, which would mean that we concluded that there were not more shark attacks this year when in fact there were. Remember, alpha is the chance that we reject the null when the null is true, or the chance of a type 1 error. This is the number that is set by the researcher when we do a hypothesis test. Typically, alpha is set at 0.05 or 5%. And then beta is a chance that we retain the null when the null is false. And again, that's the chance of a type 2 error, which is, and power is 1 minus beta. And remember, we can do a power analysis prior to beginning a study that would help inform us about the sample size that we would need to detect differences. In this case, the power is determined by the size of alpha, which again is typically 0.05, the sample size, and the estimated strength of effect. So the stronger we think the effect of our intervention or our study will be, the fewer number of people we need to have in our sample. Remember, when we look at a correlation table, each of these is indicating the bivariate correlation between two variables. And bivariate correlation can go in either direction. So it doesn't matter if we say the effect of intelligence on achievement or the effect of achievement on intelligence, it would conclude with the same number. So, and again, in the first one, all of the ones along the diagonal just indicate that it's the same variable. So obviously, a correlation of a variable with itself is going to be 1.0, or a perfect correlation. This 0.40 indicates this is the correlation of IQ, which is measured by the k-bit, and achievement, which is in kindergarten, which is designated RK. This is 0.40 correlation. That star next to it means they did a significance test, and that 0.40 in this sample is statistically different than 0. It's a statistically significant correlation. And it's a medium effect. We would classify 0.40 as a medium effect. So achievement and ability, or IQ, are moderately correlated with each other in this sample. We can look at this 0.49. This is the correlation of reading and math achievement. And it's significant. Again, remember, it's what that star indicates that 0.49 is also statistically significant, meaning that it's not 0 for our population. And it's a medium effect, again, larger than the effect of ability and achievement. So again, we can also say that students who are good at math tend to be good at reading to a moderate effect, which again probably makes sense if we think about that anecdotally. The strongest effect in this entire correlation matrix is the correlation of math achievement in kindergarten with math achievement in first grade. That's a 0.70 effect. We would classify this as a strong effect. And again, it's statistically significant. And this is something that you'll see over and over again in educational research, that prior achievement is the greatest predictor of current achievement. Remember, this is our simple linear regression equation for an entire population. What we have is our dependent and independent variables. And the difference between correlations and regressions, right, is that a regression has some indication of a manipulated variable, or we're really looking at the effect of one thing on another thing. Doesn't mean that it's causal, but we are looking at one variable that we could change and one variable that would change based upon the change we made in the independent variable. So hours of sleep on reading achievement, or amount of push-ups and weight loss. This is the population slope. So this is the extent to which y is predicted by x. When we start getting into more complicated regressions with multiple regression, we'll see that we can have various betas and x's together, indicating that more than one variable might influence our dependent variable. B beta 0 is the population intercept. So that is the value of y when x is 0. And E, this is the error that's in the equation. We separated the intercept from the error because we know that error is something that will vary by observation. So that error is the observed value of y and the predicted value of y, the difference between those two. And again, we know that in working with people, we'll always have error. And our goal in a regression equation and in an experiment would be to try to reduce that error to the greatest extent possible. Remember, when we're doing linear regression, we're going to make a few assumptions. The first assumption is that there's a linear relationship between the two variables. We almost always make this assumption, but just know that sometimes things are not linearly related, but exponentially related with a curved line. Things like growth of reading scores in young children and those kinds of things. And if our data isn't linear, then it won't fit a line very well, and therefore our conclusions will not make sense or be valid. We're also assuming that there's independence of the variable of the error in x and y, which means that we're going to assume that x and y aren't related in any other ways except through the relationship that they have with each other. That is oftentimes not a valid assumption if we're missing some variables in our equation. For example, the relationship between shoe size and reading scores is, of course, missing the variable of age. Homoscedasticity of the errors means that the errors, the amount of variation from our observation point, doesn't vary across values of x. So we don't have greater accuracy with lower numbers and less accuracy with higher numbers, or vice versa. And the normality of the error distribution means that the errors tend to be closer to our observed or our predicted variables, and that our observations are less frequent as we get farther away from our observed. Okay, so remember, when we do a linear regression, we get r and r squared. The r value is the correlation between the two variables. That's our beta. And then r squared is our coefficient of determination. It's calculated by the error of the residuals, so the error that is not predicted over the total amount of error, squared because we want to eliminate any negative values, and then the sum of those. And so again, another way to say this is that r squared is the proportion of the total variance that is explained by the model. So it's basically a measure of model fit. It's saying how much error do we have in this model? And basically how much error do we have in our prediction of y from x. We're going to look at this because it's a way for us to predict things. So as we've done a quick little review of correlation, I'm going to ask you to do an in-class activity looking at simple linear regression. There's 2 in-class activities for today. This is the first one. If you go into the lecture files, there's a data file, an Excel file, of lecture 5. There's 2 variables in this data file. The first one is reading achievement in column B, and that's 3rd grade reading and comprehension test on a 100-point scale. So you'll see the scores range from 0 to 100. And then this column C is attitudes about reading, which is a 10-item survey regarding attitudes about reading. The score is the mean of those 10 items, and each item was on a scale from 1 to 5, a Likert type scale. The higher the score means the more positive attitudes they have about reading. In the data file in Excel. You're going to use either SPSS or Excel to calculate the correlations between the 2 variables and the r squared value. If you want to use Excel, there's a website right here that can give you a tutorial on how to calculate R-squared using Excel. Otherwise, many of you were saying that you can use SPSS and you can use that at home, so you can go through SPSS to analyze these correlations and R-squares, and you can use the PowerPoint slides from last week that takes you step by step through that process. After you've completed the analyses, I want you to answer the following questions. So based upon these two variables and completing a correlation in R-squared, what's the research question we were asking? What's the correlation between the two variables, and what's the coefficient of determination? The third question asks, is the independent variable a good predictor of the dependent variable? And be sure that you identify from the data which was the independent and dependent variables in this answer. And then the fourth question is, write a 1 to 2 sentence conclusion based upon this data. So based upon the analyses you just completed, what can you conclude? Submit your answers in the comments section in the Word or as a Word document in that assignment. So you can either write it all up in a Word document and attach that file, or you can copy and paste it directly into the assignment. Either one is fine. And just remember, this isn't a grade for your final grade. It's just going to be counted as part of your participation points, and it will also be half of your attendance grade for this week. Okay, now we're going to do another little review about descriptive and quantitative statistics, just so we can kind of keep all of these paradigms in our head as we move forward. Starting from this week, we're really going to be talking a lot more about specific analyses, so I want to make sure that we have a really good foundation for what we're learning. So we have types of quantitative scales. So these are ways in which we can look at data and the types of data we might be collecting. So the first type is nominal. Remember, these are data that are categories with no ranking. So gender, sex, race, teacher assignment, these are all just groups of people, but one is not better than another, and one is not more or less than another. These are just groups. Typically, we can dummy code them as 0 and 1. So often in an experimental study, 0 would indicate the comparison group and 1 would indicate the group that was receiving the intervention or the treatment. The next one is ordinal. In ordinal, these are categories that have a rank order. So class, track, grade level, things that there is a hierarchy between them. We could also think about higher level of education might be ordinal, groups of ages might be ordinal. Interval is continuous data with no absolute zero, so knowledge from a test score, interest in the topic. In this kind of data, there's not necessarily a zero, so even if you got so like a test score of 25, a test score of 0 is a little bit meaningless. It doesn't mean you have 0 knowledge on the topic. It just means you got 0 questions correct. That's what we mean by no absolute 0. We want to retain the continuous level of this data. So when we have continuous data, we almost never want to categorize it and break it up into an ordinal scale. So sometimes, like with age, it rarely makes sense. We have a nice continuous variable from 0 to 100. We very rarely want to break that up and say 0 to 18, 18 to 25, 25 to 35. We lose some of the data that way, and it makes our analyses less valid than if we just kept it as continuous data. And then finally, ratio, and this is continuous data with an absolute 0, so that 0 actually means something. This rarely actually exists in educational research. We tend to have interval data in that the scale is a range of scores, it's continuous, but rarely does a 0 mean an absolute 0 on our scale. Okay, let's talk a little bit and do a quick reminder about measures of central tendency. Remember, this is we use this for continuous level scales. So we can't really calculate central tendency if we have ordinal or categorical or nominal data. And this is because it doesn't make sense to take a mean of groups, right? Because the group number is not a meaningful number. And it doesn't make sense for ordinal data because the difference between a high school degree and a college degree, while those might be the same level on in an ordinal scale, that doesn't make sense to take a mean of those data. Because halfway between high school and college is not really what you're taking there because it's groups. This is why it's important to keep that continuous data continuous when possible. Remember, mean is the arithmetic average. You can use Excel to calculate mean using the average function. Median is the middle number if you've ordered it from smallest to largest. And we can calculate with the median function. And mode is the most frequently occurring value. And again, if we have an Excel formula for mode. When would we use which? And I want you to think about that for a minute. We most often report mean when we're looking at our data. However, mean is highly susceptible to outliers, especially if we have large outliers. For the example, if we're all in the classroom and I ask for the mean income, well, I'll be pretty close, but then if Bill Gates comes into the room, that's going to make our mean a lot higher and not representative of our sample, the people in the room. This is where median is a much better indicator of our income, our typical income in the class. Even if Bill Gates comes into the room, our median is not likely to change very much. Along with measures of central tendency, which tell us about the typical person in our sample, measures of variability tell us how like our sample is to that typical. So it's useful in, again, continuous data. It doesn't really help us describe ordinal or nominal data. We can use variance, which is averaging the squared distance of each value from the mean. And again, there's an equation for that in Excel. And we talk about variance in that we're usually describe variance in our different models and research. We're trying to describe why people are different from each other or why observations are different from each other. But if we want to interpret that variance, we often use standard deviation by taking the square root of the variance. The reason we do this is because it helps us put it back into the original units. So variance is difficult to interpret to determine what it means, but in standard deviation, because it's back in the original units, because we're taking the square root, that helps us say, oh, if our standard deviation is 50 points, that means that the average person was 50 points away from our mean. And then range is just the difference between the smallest and the largest scale. So we can calculate that in Excel by having the max and the min and then subtracting the 2. Range, again, is the most highly susceptible to outliers. So while the range tells us the absolute dispersion of scores in a large data set, it's not very helpful. I, however, calculate range when I'm trying to clean up my data, because oftentimes if the range is larger than it should be, it means that there was some data that was entered incorrectly into my spreadsheet. So I always do a quick range check just to make sure that I don't have any anomalous data, like 1,000 instead of 100 because I hit a 0 an extra time. And then we can look at correlations. Remember, correlations help us describe the relationships between two variables. It can be categorical or continuous, but it typically tends to be continuous. Remember, it's a measure of effect size, so that can range from -1 to 1. So those correlations can really be used as an absolute determiner of how strongly two variables are related. Close to 1, remember, represents a better positive, 0 means no relationship, and then -1 means a negative relationship, right? And you can use the function in Excel to calculate those correlations. So again, here's a map of two different correlations between two things, two different variables, and we can look, just by looking at the data, we can see that correlation of 0.95 is a much stronger correlation. We can really draw a line through that data in our mind's eye pretty easily. And that correlation of 0.15, when we look at those data, it really It's hard to draw a line through. If we did, it would be pretty parallel, pretty straight horizontal. There's not much of a relationship between those two variables. And it's helpful, again, to visualize data when you're analyzing it, to take a look visually to see, are these data linearly related? And then when we're doing our calculations, we can really see if that makes sense. Okay, now we're going to do a little more talk about measurement. So again, how do the aims of science, theory, behavior, hypothesis, qualitative and quantitative research designs relate to each other? So again, we're just going to be talking again today about how we can measure things and what does that measurement mean. So remember we talked about validity and reliability last week, or 2 weeks ago. The threats to internal and external validity. Remember, we're looking to make sure that in validity that our results are consistent with each other and with our construct, and that we can generalize it to a larger population. Typically, the more we can generalize, the less we have internal validity. And the more internal validity we have, the harder it is to generalize those findings. Remember, we can look at validity as content, construct, and criterion validity. And in general, in validity, what we're talking about is, am I measuring what I want to measure? And can I make interpretations based upon that? And then reliability is the consistency of the measures that we're using. We cannot have validity without reliability. If our measures are not consistent, then we can't make conclusions based upon them. Whenever we're collecting data, we'll talk about a couple of different ways in which we have data for our research projects or for the research that we're collecting. The first one is through systematic observation in a particular setting or settings where behaviors are observed. So this is probably the most straightforward way to collect data. There's two basic types. One is direct observation. The observer is present and keeps records in real time. I did a study one time with direct observation where I went into a child care center every week for an entire year, and I recorded the centers that the students were playing with and how long they played in each center. So for an entire year, I have observational data on children. And then we also have recordings or trace data. This might be where the observer may not be present, and the records can be maintained. So through audio, video logs, files, we might be looking at Twitter feeds and counting the instances of a certain word. That would be a recording, so to speak, of some data tracing. If I was looking at computer logs or how many times my students accessed assignments in my Canvas course, these are all kind of recordings or trace data. We could also look at I could also record behaviors myself and go back and observe that and do that systematic observation, or other people, or I could take recordings that were kind of archived and use that for my data analyses. Observations generally require some sort of coding scheme, so I'm maybe deciding how to classify that behavior. So for example, in the study I was looking at with the kids playing in centers, I was also coding if they were playing by themselves or with one other person or in a group. So I was looking at the social aspect of their play. And if you know anything about child development, some of that play was interactive and sometimes it was parallel. So if two kids were playing with blocks, but they weren't interacting with each other, but they were in the same center, that's parallel play. Whereas if they're interacting and they're building something, co-constructing it together, that's another level of social play. And I had to code how the kids were playing together, not just which center they were in. And in that study, we had multiple observers across several classrooms, so we had to do some inter-rater reliability. Before we started this study, we all went in and observed the same play for an hour and calculated that inter-rater reliability. And we were looking in this instance of something above 0.9 for that inter-rater reliability, to know that everybody in the study was coding those behaviors in the same way. In addition to directly observing behaviors, we can also have surveys, or we are asking students or people, subjects, to self-report about themselves. Again, sometimes this might be if we're measuring attitudes, beliefs, or behaviors without observing them. So in some things that we measure with surveys, we can't observe directly. Like I can't observe your self-esteem, right? I have to ask you, what is your self-esteem? How do you feel about yourself? And sometimes we can't observe the behavior because it's not something that we're privy to. So we ask people to self-report on that behavior. So for example, if I was asking adults to report how much alcohol they drink, that might not be something I probably can follow around a bunch of adults, for a month and observe how much they drink. Instead, I might just ask them to record on their surveys how much they drink. So some advantages of that is it's much cheaper than observing. So I can mail out the surveys. I can do a computer SurveyMonkey or Google Forms or Qualtrics to put out there. They're generally pretty easy to score, especially through the computer. That data just comes automatically in a spreadsheet form, which gives us the potential to have a larger sample size. So in general, survey research tends to be faster, easier, and more efficient. Some disadvantages, though, there's lots of disadvantages. There's lots of reliability and validity issues to the items. We'll talk more about that later, but in essence, when we're asking questions, there's questions of validity in that are people interpreting that question the same way that I intended it to when I asked it? Are my questions clear? Do people reliably answer surveys? So in a construct like self-esteem that we would assume to be fairly stable over time, is that subject to the mood of the person, which wouldn't be stable over time? So if I'm in a sad mood, do I answer my self-esteem questions lower than if I'm in a happy mood? And it's very difficult to infer causation unless it's experimental. So again, if I ask people how much they drink and I ask them how depressed they are, I could have a correlation between drinking and depression, but in no way would this be a causal relationship, right, between drinking and depression. The only way we could do this is if it was a pre-post design. So if I had a measure of depression and then I did an intervention and then I had a measure of depression again, that might be a little more evidence towards causation, but we still might have issues with reliability and validity. Also, it's advisable to pilot your survey first before your study. And then in designing your survey, there's lots of research and questions about positively and negatively worded items. So that could be things like, I enjoy learning math and I hate learning math, or I do not enjoy learning math. When scoring those items, of course, the negatively scored items should be scored reverse. So if it was a scale from 1 to 5, then on the I hate math, the 5 would actually be a 1, the 4 would be a 2, etc. There's some evidence that perhaps you should have an equal number of positive and negative worded items, that you should alternate between them or have bipolar adjectives so that you're kind of balancing it out. However, there's some other research that suggests that negatively worded items can be problematic and that people don't answer them diametrically opposed as you might expect. So people are less likely to have strong opinions about negatively worded items, and they might be hedging their bets. It's sometimes hard to determine, if I don't agree that I don't like math, what does that actually mean? So there's some interpretation issues. So lots of times when we have negatively worded items, what we find is that they don't correlate well and they don't have internal consistency with the positively worded items. So honestly, I think it's also advisable not to include negatively worded items, but to have all of your items measure in the same direction. You tend to get more consistent results. Okay, measurement scales. So the quantitative data you collect may come in a few different flavors. Categorical, again, we talked about this. This is nominal or ordinal. So that might be asking people like, what level of education do you have? What gender are you? How many math classes have you taken? Or which math classes have you taken? Those kinds of categorical, are you a sophomore, a freshman, a junior, a senior? Those are all categorical data. They can help you put people into groups, especially if you wanted to compare group differences. So do freshmen have higher university engagement than seniors? And then continuous or ordered data, interval and ratio. So ordered data with numerical values or interval. Most of the time we include Likert scales of this interval continuous data. So even though it's not truly continuous and that someone isn't answering 1.255, they're answering 1 or 2 or 3 or 4 or 5, we still consider that continuous data, especially for taking a mean across several items. And again, the key here is to keep continuous data continuous. So if I'm asking age, I don't want to then group age into categories. If I'm asking students about their attitudes towards math, I don't want to then group them between people who enjoy math and people who don't enjoy math. Instead, I want to keep that a continuous range because in all likelihood, people who don't enjoy math have different degrees to which they don't enjoy math, right? And if I put them all into one group, then I'm losing that nuance of data and my results might come out differently. So if I had a lot of people in that don't like math group that actually just kind of didn't like math, I might not see a difference in math scores when in fact there was a correlation between the degree to which they enjoyed math and their math scores. Survey response format. So in our surveys, we have a couple of response formats that are possible. Di or trichotomous data, which would mean things like, do you like math? Yes, no, I don't know. That would be 3 choices. So we're really asking people to make a choice between a couple of options. We also almost always, when asking questions about group membership, are this kind of selection ideas. Ranking items. In this type of question, we have a list of things and we're asking our participants to put them in order. So I might have a list of subject areas and have them rank them from my most favorite to my least favorite. Or if I'm, a Likert scale or a Likert type scale, that's those agree to disagree. So in Likert scales, you want to have an odd number. So you have 1 is strongly disagree, and let's say 5 or 7 are strongly agree. You always want to have a middle value that's neither agree nor disagree, because there will be people who really don't feel one way or the other about the topic or the question, the item. And if you force them to choose that they agree or disagree, then you're losing some validity in your data. So I always encourage students to have an odd number of answer choices on those Likert type scales, and to keep that agree to disagree scale from 1 to 5 consistent throughout your survey. So always make the 1 disagree and the 5 agree in all of your scales. For younger participants, you want to have fewer choices, but for older participants, you can have more. The longer your scale is, so if you have 5 or 7 or 11 choices, the greater degree of nuance you'll get, but you're also increasing the cognitive load of the survey. So many times you probably want to keep it at 5 or 7 and not really go over that. Continuous scales, that's like having a 100-millimeter line on a paper, and where students or participants can mark where they think they fall on that line or that scale. In Qualtrics, you can actually have a moving button that kind of goes across the scale so they can really have more nuance in that. And that produces more continuous measurement that is maybe perhaps a little more valid than a Likert type scale as far as accuracy and really making that difference between ordinal and continuous really important. If you're doing something in Qualtrics or on the computer, then that data is really easy to translate into your into a spreadsheet. It will automatically do that. If it's a paper survey, then you have to get out a ruler and measure, which is probably why researchers tend to use Likert scales more often. Magnitude scaling is similar. And then, so along with surveys, we can also have tests. Tests are measures of what people know with right or wrong answers. So much of what we apply to surveys also applies to cognitive tests or achievement tests. If you took my master's level class on assessment, we spend much more time on this than we will on this class. You're asking participants to complete some sort of cognitive task by responding to a standard set of questions. And again, you can have lots of item types. You can have multiple choice, short answer, matching, essay, fill in the blank. And those response scales might be dichotomous in that either the student gets them right or wrong, or they might be rated subjectively on a scale, from 1 to 20 points, perhaps available on an essay. What can you do with those test scores? There's two ways. You can't just say, what does this mean? A 90, what does this mean? It needs interpretation. The first option is norm referenced. So this is where individual scores are interpreted relative to other scores. Sometimes that's a normed group. So if we say something like you're in the 95th percentile of your class, or you're the 95th percentile in IQ, that means something. It means you scored 95%. You scored better than 95% of whatever population we're comparing you to. We often see norm referenced scales when we're looking at things like IQ or even achievement across maybe a state or an entire country or a representative sample. We could also norm reference our group. So if I had in my study a group of people who took this test, I could see how far away, and that score might be based upon how far away they were from that norm, or the average score. And then option 2 is criterion referenced. This is most often what you see in schools, in that the interpretation is the number of items they got correct or relative to some sort of standard or criterion. So if I have a measure of 3rd grade achievement and they scored a 95%, that would mean that they've mastered 95% of 3rd grade math. And it's really important that when you're looking at scores and you're interpreting them, that you make that distinction between norm and criterion referenced. So again, norm reference means I'm comparing your score against a group, and criterion reference means it's compared to some sort of standard. Most grades in school are criterion referenced. If you get an A in my class, that means that you mastered most of the material for the class, right? If you fail a class, that means that you did not master the material for the class. You did not understand it. And then norm referenced would be more like class rank. So you were in the 25th percent of your class in achievement. And again, all measures, we can think about the reliability and validity of measures based upon the interpretation and the sets of scores that we have. The validity of the observations. So when we're looking at observations, does the behavior observed and coded match the construct of interest? So was I coding data in a way that made sense to my construct? So if I was looking for, let's say that I wanted to know if students were on or off task during class, right? And I operationalized that. I was observing behaviors of whether or not they were in their seats or out of their seats. Is that a good match to on-task behavior? Maybe, maybe not. Are there ways in which kids could be out of their seats and still be participating in class? And are there ways in which kids could be sitting in their seats but still not engaged? And then the reliability of the observations. So that would be when I observed that behavior, was I observing it in a reliable way? So if a kid was sitting on the floor, does that mean he wasn't in a seat, or does that mean he was in a seat? And if another observer was using the same scale, would they measure that behavior in the same way? So is it consistent? And that really depends on how well I operationalized, how well I said what that behavior consisted of. And then the validity of surveys and tests. So again, do my items measure my construct of interest? So if I'm asking questions about enjoyment of math, I can say I enjoy doing math in my free time. I enjoy going to math class. I look forward to math class each week. Math is one of my favorite subjects. All of those really measuring the same thing in the construct of interest. And then reliability of surveys. And there's kind of two ways to think about this. One is, do the participants respond similarly among items? So I want that internal consistency. Do all of if I have 10 items about enjoyment of math, then the scores on those items should all be similar. I should have a strong internal consistency. And then there's other things that can affect the reliability of surveys, so fatigue. So if my survey is 100 questions long, by the end of the 100 questions, people are tired of answering and they're probably no longer reading the questions carefully and answering truthfully. There's also social desirability. So if I ask people how much they drink, and if I'm asking my students, you guys might give me a socially desirable response. You might be less likely to respond with the actual number of drinks you have a day, and maybe lower that number so that maybe I might look at you better. And the degree to that socially desired response can affect a couple of things. One is how sensitive the questions are that you're asking. So if you're asking pretty benign questions, you might not see a great effect of social desirability. It also depends on the relationship with the surveyor. So if it's anonymous and I don't know the person conducting the research, I'm much more likely to give honest responses than if it's my teacher or if my name's attached to the survey. So if it's a math teacher and she asks you how interested you are in math, and you put your name on the paper, you're much more likely to say that you're really interested in math when you're not, right? Because you think that there might be a consequence to how you answer the survey. And then finally, complex and unclear wording can lower the validity of our survey, in that if I don't understand or I think the question's asking something different, that I might not be getting a really valid response. And this goes back also to those negatively worded items. If I disagree that I don't enjoy math, and that means I enjoy math, but that kind of logic can get pretty confusing, especially for younger survey participants. The validity of tests. So when we're looking at those tests, there's just content validity. Really looking at, do those items measure and are they all about the construct of interest? And then we have something we call item sampling, or do these items represent the domain as a whole? So if I go back to, I'm making a test about third grade math, but I only have addition and subtraction questions about third grade math. Well, we know that in third grade, you also learn about geometry and shapes and area and perimeter and measurement and fractions. So if I only include items about addition and subtraction, then I'm missing a lot of third grade math, and my test probably doesn't really measure all of third grade math. So when I think about that, does the sample of items I put on my test, does that measure the construct as a whole or just part of that construct? And then the reliability of tests. Again, do participants respond similar among similar items? So if I have a bunch of addition questions, students who understand addition should get those addition questions right, and same with geometry or measurements. So do participants respond similarly among similar items? And there's lots of ways that we can calculate this reliability. On tests, we can do some item analyses, which is much more complicated and way out of the scope of this class, but is a fascinating topic for future discussions. And again, we have some item type examples. So, do you believe Pluto is a planet? List everything you know about bear hibernation. Number of times the child shares in an hour period, let's say. And which of the following is a true experimental design with A, B, C, and D? So again, thinking about how would I score this on a test? So the first one's obviously an open response essay type question. So I'd have to have some kind of rubric or consistent way to score that. And that inter-rater reliability on this item is going to be really important. The second one, list everything you know about bear hibernation. I'm going to have to do some sort of validity check to make sure that what they list is correct. But I also might be counting how many things could they list that were correct. But if people only listed 5 things, does that mean that they only know 5 things about bear hibernation, or did they get tired after they wrote 5 and didn't write any more? List the number of times a child shares. How am I going to operationalize that? When I'm looking at sharing behaviors, does that mean that they were playing in parallel, or that they gave a toy to another child, or they were both able to play with it? This would be sharing, again, is not something that's easily defined when I'm observing behavior. I'd really have to think about how I could get reliability of those observations and coding. And the last one is a multiple choice question, right? So we would assume that there's only one correct answer, but then let's look at answer D. Frank Lloyd Wright's falling water. That is, in fact, a type of experimental design, right? He was using design principles of architecture in an experimental way, but it's certainly not what we mean in a quantitative methods class by experimental design. So again, we'd really have to think about how these questions might be interpreted by our students, and if when we are creating those item choices, what would be assumed correct or incorrect, and what that context would be. Okay. So if we're looking at kind of our conclusions for today, what are our insights, thoughts, and questions based upon what we've talked about today? Has this helped you frame your analysis project and moving forward in this class? And how does measurement relate to these aims of science and theory and hypotheses? And thinking about this in both qualitative and quantitative research designs. And then, so our last in-class activity is going to be about measurement. And again, I would like you to create 3 sample items here to capture each of the following data types. So write me a question that would have continuous data, one that would have ordinal data, and one that would have nominal data. And again, you can submit these answers, just copy and paste them directly into that comment section of the assignment, or you can attach the Word document. Either way is fine. And again, this assignment's not going to be calculated as part of your final grade. However, it will be your participation points for today and also as half of your attendance for this week. So if you have any questions about this, feel free to email me throughout the week. I will have email even though I won't be in town, and I'll have it on my phone. So I will certainly be checking it this week. And just as some reminders, your in-class activities will be due Wednesday before our class next week on Thursday, along with the reading reflection on NAGI, which would have been the reading for last week. Upcoming, on the 21st, you'll have the reading of Mills, and also our first out-of-class activity will be an analysis using simple linear regression and t-tests. We'll talk about t-tests next week in class, but if you want to get a jump start on that class activity, you should be able to start looking at that SLR. The readings for this week are the Mesic, Cronbach, and Crocker analgina readings. That's 3 readings, but again, just make sure that you understand the Cronbach, and particularly will help provide some foundations and some supplementations to the lectures this week. And then as your analysis project, you should be collecting data now. You should be in that phase for your project. If you have questions or if you want to confirm what you're doing, please let me know. I'm happy to chat with you, and I've chatted with certainly many of you already about your projects. So some of you already have data collected from a previous class. Some of you have access to data as part of your job that might be a really relevant problem of practice. And some of you are kind of starting over and thinking about ways in which to collect data for this class. So let me know how you're doing, and if you have any questions, again, please email me. And again, I'm sorry I couldn't be in class this week. I miss seeing you guys, and I will see you on the 15th. Have a great day. Bye-bye.